Hi, I'm Mark Weitzman, and welcome back to this series of videos on a problem from the MISISx Russian MOOC on complex analysis. So last time we had computed the function h of z, which is our multi-valued critical part of our function f, at the poles, and we found it's equal to this formula here. So what I want to do now is to find the value of f of z at each of these poles. So let's just substitute f parentheses z. Let's look at the first potential pole, z equal. Remember, right now we're still working on the first sheet. Now this is equal to, let's just substitute in this value. So we have a 1, and we have 1 minus this thing cubed, e to the 2 pi I over 3 cubed is 1, so we're going to get left with, I'm sorry, okay, we're just going to substitute in, not going to substitute into z, but we've already established that it's this value. So it's 1 over the cube root of 2 e to the 2 pi I over 3 minus the value of the pole here. Minus, I'm sorry, this is divided by the cube root of 2. Minus 1 over the cube root of 2 times e to the minus 2 pi I over 3. Now, whether you want to simplify and turn these into sines and cosines doesn't matter to me because we don't know, but the main thing is this does not vanish because we have a plus here and a minus there. So this is not a pole, at least not a pole on the first sheet. Sheet or branch. Okay, so now let's do the same thing on evaluated at z equal 1. Now we have the same thing. 1 over the cube root of 2 e to the 2 pi I over 3. Because we showed that all the poles have the same value for h of z, minus 1 over the cube root of 2. And again, this is the same thing. No, it's not a pole because this doesn't vanish. And now, our last one, I'm always leaving out these cube roots of 2. That's a 7, not a 3, European 7. Now here, I'm going to get 1 divided by 1 over the cube root of 2, e to the 2 pi I over 3, minus 1 over the cube root of 2, e to the 2 pi I over 3. Because that's the value, this is what z is at the pole. This is a pole. So we've established that at least on sheet 1, I just want to make sure I don't get this wrong. This pole is on sheet 1. But notice, when we compute our function, we go from sheet 1, we analytically continue across the branch cut, we're on sheet 2. So this is not going to interfere with this contour. We could bring it right over here and run right through there because this is on a different sheet. Okay. Now, let's try and compute the poles on the other sheets. I probably should keep this up, but I don't have any room, and I'm not touching this board. I never managed to become a theoretical physicist, and I still think that there are probably three main reasons why. Just a little personal aside. One is my handwriting was absolutely like the sloppiest it could be. Two, no piece of paper was ever large enough for me to do a calculation. And three, when I did go to Caltech to get my PhD, I wasn't all in the language of my subsequent professional poker career. So, as a wannabe theoretical physicist, I feel like I never have a large enough blackboard, and I never have a large enough piece of paper to do calculations. Okay. Let's start looking at poles on the other sheets. Here we draw the same diagram again. Now we start off on the first sheet of our function like this. And we're following the contour. And before we just went to here, or we went straight there. But now we're going to cross the sheet and then go here. How does this affect our delta arguments that we calculated in the video earlier? Well, from this branch point, our arrow still goes like this. And it doesn't really make a loop around. It's still pi. If it went around this point, it would, but it doesn't. And from here, the same thing. We start out like this, and we go like this, and then we go like this, but basically, it's unchanged. Exactly, it's unchanged. But for our reference argument on this one, we can see that we go like this instead of going all the way down this and rotating a little bit to there. I call that minus theta because we rotate in the counterclockwise direction. This time, this angle should be the angle between here and the angle between there, minus theta. But this time, when we follow along on the contour, we see that our thing starts off here and then it goes all the way around there. So the angle is really this. So before we added minus theta, this time when we go around this branch point, we're going to add 2 pi minus theta. And the difference is, of course, 2 pi minus theta minus theta equals 2 pi. So our reference point, and then we're going to take that 2 pi, which is for G. This is the additional delta. We're going to take that and then divide by 3. So when we look at this formula, and we're going to find that it works the same for all three poles. You can work that out yourself. But on the second sheet, we're going to find at the poles h of z is equal to e to the 4 pi I over 3 divided by the cube root of 2. Now, I want to emphasize, because I had this misconception, it's not that the phase jumps from here to here by 2 pi I over 3. It would jump by negative 2 pi I over 3 if you wanted to maintain on the first sheet, but we're going to the second sheet. We're on the second sheet. This is continuous over here. But when you make that whole loop, you end up building an extra 2 pi I over 3 phase. Before you sort of like shortcut there, and now you're going this way. So there's no discontinuity in our function. That's what we mean by analytically continued. That was a mistake I made that the professors pointed out. I've learned my lesson. So, but on the second sheet at the poles, this is the formula for the for h of z. So what do we think the poles are going to be on the second sheet? Well, I think as you can see, let me write down this thing over here. First sheet. Now I'm going to add on the second sheet at poles. This is also at poles. They're not really poles, but I'm just calling all these potential poles poles. Here we get e to the 4 pi I over 3 divided by the cube root of 2. This is what h of z is. So remember, our formula, we need to have h of z to be equal to z. So the only pole on the second sheet is going to be where this is going to be equal to the value of the pole. But now I'm confused myself. So, okay. Let's rewrite this just so I don't get confused anymore. This is the same thing. E to the 4 pi I over 3 is the same thing as e to the minus 2 pi I over 3. So the pole on the second sheet is this one over here. And that's great because that doesn't interfere with us continuing along and deforming the contour to the line and integrating along the line, which is what we'll eventually do. And as you can imagine, this pole over here is going to be on sheet 1. Because when we go around again for sheet 3, it's the same story. It's kind of like we loop again across the branch cut, you know, another loop here, and it's going to add another 2 pi I over 3. So on the third sheet, it's just going to be h of z at all those pole points. It's just going to be 1 over the cube root of 2, and that will, of course, equal to z in here. So, as I said, I have it written down wrong. This is on sheet 3. So everything is very convenient. We can ignore this pole here because we're on sheet 1. We can ignore this pole here because when we're integrating our function, we're on sheet 2. And we can ignore this pole here because this is on sheet 3 and we're either on sheet 1 when we go below and we're on sheet 2 when we go above. So everything works out nicely. And so on the next video, I am going to start talking about deforming the contour and doing the integrals. And the whole difficulty in this problem is making sure you get the right phases right on the sheets. I screwed this up a couple of times because I kept on thinking that when I go around here it's minus 2 pi I over 3. I was thinking that, but we actually go this way, so it's different. And I'll see you in the next video. Thank you very much.